Statistics on Lie groups for computational anatomy. Lie group, Riemannian manifold, Fréchet mean, group exponential barycenter. What do those terms represent? Isn't it possible to explain them without mathematical axioms? And why do researchers use them? We made this video to present the context of computational anatomy in which these concepts arise, the context of statistics on Lie groups. To illustrate these concepts, so that you can picture them next time you read about them. To give you intuition about how to use this framework for your own research. To fulfill these objectives, let's picture the following caricatural situation of computational anatomy research. Imagine a brain surgeon visits you. He needs a software that detects if a brain has a disease directly from its image. Of course, he is looking for diseases known to change the brain's anatomy observable in images. His database of brain images is at your disposal. How will you implement the software? In an oversimplified scenario, you could do the following. 1. Compute the average brain, called the mean brain, of the healthy brains. 2. Compare a patient's brain to the healthy mean brain. If it's too different, it might be a diseased brain. But how do you compute the average, or the mean, of brains? And how do you quantify the difference between two brains? In this video, we see how the Lie group theory arises from this problem. Particularly, we compare the different options you have to compute the mean of brains. The quantification of the difference between brains will naturally arise in the framework. So, let's compute the mean of brain images. First, you need to convert them into mathematical objects. This image, for example, can be modeled as the function of its intensity values, the surface of the brain represented, the smooth transformation of a template brain, or another mathematical object. The Lie group theory arises from the third model. As the goal of this video is to present Lie groups, let's choose this model. Your data are transformations of a template brain. In terms of mathematics, they are elements of a Lie group. For now, consider a Lie group as the group of all possible smooth transformations of the template. Examples of Lie groups are the group of translations, the group of rotations, the group of rigid transformations, which are transformations that don't deform an object, the group of non-rigid transformations, or diffeomorphisms. The first three are finite-dimensional, and the fourth, the Lie group of diffeomorphisms, is infinite-dimensional. In computational anatomy, most research is done on the group of diffeomorphisms. But working on Lie groups involves a particular framework, even in the finite-dimensional case. So, let's train your intuition on Lie groups with the simpler case of the group of rigid transformations, SE3. SE3 stands for Special Euclidean Group in 3D. A rigid transformation F is a combination of a rotation and a translation, and hence characterized by 6 parameters, 3 for the rotation and 3 for the translation. In other words, SE3 is 6-dimensional. Of course, it's difficult to visualize F as a point in 6D. In this video, we show the action of F on the template brain. Now, how will you compute the mean of two rigid transformations, F1 and F2? An idea is to compute their mean as their half sum. Let's do it and show the result of the action of this mean on the template brain. Don't you think something disturbing? The mean of two brains is not even a brain. This is an example of an absurd result you get because of a theoretical error. You may look after a bug for hours, but it is not a problem of your code, it's a mathematical issue. So, what's the problem? This formula works only if F1 and F2 belong to a linear space, like this space. Why did it not work for the space SE3? Because SE3 is not a linear space. SE3 is a Lie group, and Lie groups are not linear spaces in general. What are Lie groups then? How does a Lie group look like? take the mathematical definition of Lie groups now. It's a manifold that is also a group. And a manifold can be curved, so a Lie group can look curved, and SE3 looks curved. Good news is, you can generalize what you learned on linear spaces to manifolds. For example, you can also define vectors on the manifold M. But each vector is attached to one point P and belongs to the tangent space of M at P. On the linear space V, tangent spaces at different points are the same and equal the whole space. On the manifold M, two tangent spaces at different points are fundamentally different. Now that you know that SE3 looks curved, can you guess why you didn't get a brain when you computed f1 plus f2 over 2? You had your two data on the curved manifold SE3, and you computed their mean in this linear way. This mean is not on the surface SE3, so it is not a rigid transformation. That's why its action on the template does not look like a brain. Conclusion: you can forget about computing the mean like this. You need to use another definition of mean if you want to code the software for the surgeon. What about using the definition of Fréchet, the Fréchet mean? The Fréchet mean is a definition of mean that works on manifolds. Fréchet took a property of the mean on linear spaces and made this property the new definition on manifolds. He remarked that on linear spaces, the mean minimizes the sum of the squared distances to the data. So, on manifolds, he defined the Fréchet mean as the point realizing the minimum of the sum of the squared geodesic distances to the data. Wait, geodesic distances? Yes, to compute the Fréchet mean on SE3, you need geodesic distances. And for that, you need a new tool on the manifold, a metric. To understand the metric, let's generalize from the linear space to the manifold. On the linear space V, you can define an inner product. You get a Euclidean space. On the manifold M, you can also define an inner product called a metric. But remember that tangent spaces at different points are different, so the metric depends on the point P. You get a Riemannian manifold. Now, on the linear space V, the distance between 2 points is the length of the shortest curve linking them, the straight line. On the manifold M, the geodesic distance between 2 points is the length of the shortest curve linking them that lies on the manifold, which is called a geodesic. Now remember, for your software, you need to quantify the difference between two branes. This can be done with a geodesic distance. The more different two branes are, the further they should be from each other on the Riemannian manifold. Now, let's compute the Fréchet mean. For that, you need a metric on SE3, which will quantify how rotated and how translated two branes are from each other. There are at least two families of metrics fulfilling this, called the right invariant metrics and the left invariant metrics. We don't go into details here, just remember that they would be equal if SE3 was commutative. Let's choose one metric of each family. Look how different the metrics are. They provide two different geodesics between f1 and f2. So, they provide two different notions of geodesic distances. And if you compute the corresponding Fréchet means, you get two different results. But now, they look like branes. So, given only one metric, the Fréchet mean seems like a reasonable option to compute a mean, don't you think? Now look carefully. Remember, your brain data are elements of a Lie group because they are transformations of a template. Imagine you change the template. You get a new dataset of transformations, right? So you can compute the Fréchet mean of these transformations and show the result of its action on the new template. Do you see the problem? The new Fréchet mean is not consistent with the previous Fréchet mean. Even if computed with the same metric, the branes don't look the same. Why? To perform the change of template and compute the new data, you use the composition and transformations of SE3. So, you use the group aspect of the Lie group SE3. Can you guess now why two different templates give two different Fréchet means? Because the Fréchet mean was defined regardless of the group aspect of SE3. It's a definition for Riemannian manifolds. So, it does not respect the group logic in general. We say that it is not group consistent. Now, let's define a mean that respects manifold and group aspect of Lie groups. The group exponential barycenter. The group exponential barycenter is a definition of mean for Lie groups. Again, take a property of the mean on the linear space and make it the definition on the Lie group. The group exponential barycenter generalizes the property of the mean to be the barycenter. Wait, why group exponential? And what is this log here? Yes, to define the group exponential barycenter, you need to generalize again some notion from V to M. But now M is more than a manifold, it's a Lie group. Let's write it G. On V, you can add a vector V to a point P, or subtract P to Q to get V. On G, this generalizes to the group exponential of V at P and the group logarithm of Q at P. They are called exponential and logarithm because in the case of matrix Lie groups, they correspond to the matrix exponential and the matrix logarithm. Note that, on Riemannian manifolds, you can define Riemannian exponential and logarithm, even what we call a Riemannian exponential barycenter, but those notions are different. Now, let's compute the group exponential barycenter. If you show the action of the group exponential barycenter on the template, you get this. It looks like a brain, and if you change the template, it's consistent. So, you think the group exponential barycenter is a good option for your software? Why not? But how do you quantify the difference between brains now? You don't have any metric. The surgeon is back, and he wants the software you promised. What do you deliver? Let's summarize your options. The two reasonable choices are the Fréchet mean, a notion for Riemannian manifolds, and the group exponential barycenter, a notion meant for Lie groups. With the Fréchet mean, the drawbacks are there are a lot of different metrics that give you different results. If you change the template brain, you get another result. The advantage is that it comes with a consistent metric that enables to quantify the difference between two brains. With the group exponential barycenter, the advantages are you don't need to think about a metric. If you change the template brain, you get the same result. The drawback is that you don't have a natural metric to quantify the difference between brains. There could be a way to take all advantages without the drawbacks. Do you see it? For example, a metric such that the corresponding Fréchet mean is the group exponential barycenter. But does such a metric exist? For some Lie groups, like the group of rotation SO3, the answer is yes. There is a metric that makes the corresponding Fréchet mean the group exponential barycenter. But for more complex Lie groups, like SE3 and the infinite-dimensional Lie group of diffeomorphisms, the answer is no. You have to choose between a Fréchet mean or the group exponential barycenter. We have reached the end of the video. What are the take-home messages? There exists a framework in which your data are modeled as transformations of a template. This is a situation where the Lie group theory arises. The example of Lie groups illustrates the fact that statistics depend on the nature of the data space. The example of SE3, the group of rigid transformations, provides intuition for other Lie groups, like the group of diffeomorphisms commonly used in computational anatomy. And finally, we took the example of the mean, but the same kind of discussion arises if you want to do principal component analysis on Lie groups. That's it! Now it's your turn to explore Lie groups. Good luck!